deliveries of cigarettes produced in Soviet Union are important to the country. First, the tar deliveries declined to 15 milligrams per cigarette and later to 12 milligrams per cigarette. I would like to draw your attention to this graph. Here we see trends in lung cancer mortality in Russia and three countries, former Soviet republics, Kazakhstan, Latvia, and Ukraine. As you see, the turnover in lung cancer have occurred in the same time. And that suggests that the cause of this turnover of the mortality curve was the same, the decrease in tar levels of cigarettes produced in Soviet Union and imported to Soviet Union. The decrease in mortality from lung cancer since 1993 only in Russia saved lives of some 250,000 men and women who otherwise a lot of things to do. I hope that we will be able to achieve that. And if you are seriously decided to retire, you are invited to join us in Moscow University and Moscow Cancer Research. If you are really serious about retirement, thank you.
Thanks, David. Now we're...
This is 1985, and this is 1910. This is a very important slide. It is taken in Siberia. This is in Lyon. This is trivial, but this is Siberia. Thank you.
Thanks very much, David. Now we're moving to China, and Zhenming Cheng, who's again a long-standing worker, long-standing collaborator of Richard's, talking about the long... Sorry, Cheng. Okay. Zhenming Cheng.
Good afternoon. It's a really delight to be here to celebrate Richard's first retirement. I've been waiting for this for the last 2 years, not because I want to see Richard leaving. It's complete opposite, because his new office is right opposite to mine. So I should be able to work more closely over the next 30 years. I first met Richard in 1987 at the tobacco conference in Tianjin with the medical students, and over coffee break, I just volunteered myself and approached Richard. And subsequently, he said he wanted to come to talk to me more to Shanghai. And then after that, he said, come over to Oxford for a year. I couldn't believe this is real. I said, it must be joking. I never know him. He's such a famous professor. And after just maybe a couple of hours discussion, he offered me to come to Oxford. It's like dream. But today, I'm still here after 30 years. So with this title, I hope to give you a brief account of extraordinary collaboration in China, which was initiated by Richard and Rory started in the early 1980s, which is still continuing and also growing as well. I mean, taken together, they probably represent some of the largest and longest medical research in China. This study covers primarily chronic disease, non-communicable disease, because by the time Richard went to China, it was too late to study them. So as shown, this slide shows the patterns of mortality in China. 2010, that 9 million deaths at all age, only 400,000 from communicable disease, half in the childhood in the poor rural areas. 0.8 million injuries, but 8 million out of 9 million due to a wide range of non-communicable disease. Half actually die in middle age. 2 million from cancer, 2 million cardiac, 2 million stroke, and 1 million COPD. I stole this slide from Richard and show his typical style, big, bold, very easy to read. So this is actually where we are now. Can we halve them? To what extent they compare with the past and with the rest of the world? So again, this is a part of Richard's work, shows extraordinary changes for mortality over the last 40 years in some of the biggest countries. At middle age, 50 to 69. So this is China, very spectacular decrease. I think still continuing, especially among never smokers. So which is slightly behind UK, USA, but it's catching up quite rapidly. I just read some articles a few days ago by WHO. If it continues, by 2030, China will catch up with America in terms of life expectancy as well. I'm sure you all agree, Richard is a cause of these spectacular changes, improvement, not only in China, but also globally, due to prevention and better treatment for many conditions as well. But China is not uniform. There's a huge, well-documented and unexplained variations in mortalities. So as shown here with the two common cancers, esophageal cancer, nasopharynx cancer, both are very rare in UK or in some other parts of China, but they are very common in certain other areas, as shown in this red spot. And in these areas, the mortality rates probably 5 to 10-fold as high as in neighboring counties or regions. We still don't really understand because this is among female, they don't drink, they don't smoke. Apparently the known risk factors cannot explain this huge heterogeneity. I think the future will be very difficult to predict because there's favorable changes, but also unfavorable changes, particularly given the rapid rising burden of tobacco. So this shows the annual Chinese cigarettes consumption production over the last 60 years. This is the time when Richard first arrived. For the fake news, people may claim Richard is the cause for this increase. But as a matter of fact, Richard is the first Western epidemiologist to warn Chinese government about this forthcoming tobacco epidemic. I still remember many meetings, still recall many meetings Richard had with the health minister. I went together, at least 4 or 5 of them, Chen Mingzhang, Cui Li, to Chengdu. And when Richard sat down at dinner table, normally, first thing he did, reach his pocket and open up a piece of a paper with very striking figures or statistics, and to talk over through the meal. And although the meal very nice, and the day I said, what meal do you enjoy? I said, I forgot, I eat anything. So I think it's not very easy in China trying to get the momentum going on tobacco control. Even among many epidemiologists, very well known, I know, they don't believe smoking is that bad. They believe smoking kills Americans, British, but not Chinese. Chinese is somehow very special. I mean, the truth is actually, the simple fact is they fail to recognize the delayed effects, as well described this morning. And because you're not going to see huge impact, mortality, at least for another 30, 40 years. So after many talks, and Richard realized the only thing is actually try to get local evidence. So this is what we did together. Richard initially joined in 1990s, a series of larger studies. First on tobacco, case control studies, prospect studies, initially no blood, eventually blood-based, along with many other studies, larger clinical trials as well. So this just summarizes a range of studies that have been conducted over the last 30 years under the leadership of Richard and Rory. Total 9 population-based studies, total over 2 million participants. Some are just descriptive epidemiology, some are case control, and more into large, long-term blood-based prospect studies, not only smoking, but a range of other things, as well as many large-scale randomized trials, and a total with over 100,000 patients recruited. I mean, together they have generated a lot of publications, and many thousands are coming over the next 10, 20 years. But together they have a huge impact on disease prevention and treatment. And for example, and this is a Chinese cardiac study with 46,000 patients recruited from within China, and demonstrate the benefits of combined antiplatelet therapy. That's led to the change of guideline by FDA as well. So it has saved many patients' life as well. So it's not possible to go through all of them. So this is just a list of the key publications in the 4 top medical journals, plus 2 big monographs, each weigh probably 5 kilos. And so in the interest of time, I'm just going to show one particular results on tobacco because that's one of the main themes for the past, but also for the future as well. So this is a contrasting male-female trends in tobacco, which bring together two larger cohort study, Kadori, and also the early study with the 15 years apart. So help to document the evolving epidemic in China. So this is a summary. Smoking will cause about 20% of all adult male deaths now, which is an increase from 10% 20 years ago based on old evidence. And the tobacco attributed proportion of deaths is rising in men. But interestingly, completely differently, unexpectedly, it's low and decreasing among Chinese women because Chinese women are much more sensible, intelligent. And although overall adult mortality rates are falling as the adult population grows and the proportion of male deaths due to smoking increase, the annual number of tobacco attributed deaths will rise from about 1 million now to 2 million by 2030 and to 3 million in 2050, unless there's a very widespread cessation as well. I think this is based on the hard local evidence. And also prediction is very reliable because we got a subset population, they start young, they're on cigarettes, their risk is almost same as what we see in the West. But we're not going to stop here because the next paper already got agreement with Richard over the next 6 months is to continue working on this, not on mortality. For the first time, we're able to study morbidity as well. In the Kadori, we capture almost 1 million episodes of hospitalization. So we can study beyond deaths into a range of other diseases, probably 5 conditions, each with 500 different cases. So I think there will be a lot of novel findings, even for these very well-researched topics as well. So the study is based on the Kadori, which is a continuing. So this is a huge undertaking, involved over 500,000 participants, recruited in 2004 and 2008, and from 10 diverse areas, 5 rural, 5 urban, from freezing north in Harbin to tropical south, from coastal cities, well-developed to inland and rural areas, with very different disease patterns and different stages of economic development. So this is a huge undertaking, very big, but it's done very, very carefully and very high quality because over 90 different IT systems, everything the electronic, no paper involved, with a lot of data captured and baseline and the periodic re-surveys. We have done 2, and the third one is coming by questionnaire, by measurements. Increasingly, we are turning sample into the data, genetic, proteomics, metabolomics, and also linked to other data as well. And the most important things, we're now linked to not only mortality, we've got 45,000 deaths, only less than 5,000 lost to follow-up, but a wide range of other non-fatal conditions. In 10 years, we have captured almost 900,000 hospitalizations, including 15,000 cataract surgeries, 15,000 osteoporosis, fracture as well. But this has been a huge success, I have to say. But this comes in retrospect of a very long, bumpy journey. It's probably since the 1980s. I remember Richard said before I arrived, he made first application. And during 1990s, and many field application to get the funding for such a study, because no one wants to fund study. It's too big, too vague, no hypothesis, not relevant for British or Westerns, even though many people do believe the results from zebrafish or mouse results. Even when we got the funding through the help of Judith, from Kadori, I promise, we still couldn't get the approval. It took us 2 years to sort approval. And we just got a letter from foundation that said, if you don't get the permission for this collaboration, and the whole funding will be cancelled. That was actually on 10th May 2002. So although our colleagues in China tried very hard to try to persuade the ministries to prove these wonderful studies, but on the 29th of April 2002, we heard very disappointingly, and the committee decided not to approve the study. Again, the same reasons, too big, too risk, DNA, and very sensitive issues in China. So Rich and I decided to go to China. So we went there, we spent a week. We said we probably could do something. but we end up nowhere. Even Ministry of Health, Science and Technology reluctant to see us for various reasons that it's not convenient. Eventually, we got this one on the 10th of May 2002. We got approval. So it's like magic. I still remember, on early morning of 10th, which is at 2 o'clock, we had a couple of drinks. We said, tomorrow is the last day. We managed to see the Health Vice Minister, Wang Jiefu. I mean, if he got proof of us, we're not going to get the permission letter within the same day. And the Kadoorie Foundation may still cancel. So we said, well, let's pretend that we get approval. Everything goes well. Let's draft the letter, approval letter. So this is actually what we did. We worked for 2 hours until 3:30 in the morning. We draft on behalf of the Ministry of Health. So this is approval letter. And then we went to see, and suddenly, we got permission. And 5 o'clock, we got this letter, this fax back to the Kadoorie Foundation. They said, okay, the study can go ahead. So it's very extraordinary. I mean, you don't normally tell, politics is exciting, very difficult. And I've learned quite a lot from Richard through the process, how to do diplomacy in China, to be persistent and believe yourself and never give up. So this is where we are. There are many other similar stories I don't want to go through. So I think over the next 30 years, we're going to have a huge amount of research done, not only by us, by collaborators, but external researchers, and not only hypothesis testing, but also hypothesis generating as well, through conventional prospect analysis of big causes, a wide range of a disease, nested case control study, blood-based biomarker for different disease, and into GWAS, PHWAS for drug discovery, Mendelian randomization, and a wide range of things. So for the first time, we're able to study not just obvious, but also non-obvious. I think to end my talk, I just want to share one final result, and Richard, I've been working with Richard and Aona over the last 2 years. We know from David, heavy drink will kill you, and a lot of problems. But the myth over the last 50 years is moderate drinking, light to moderate drinking. And as epidemiology studies, we keep finding this J-shaped association. And this is a current drink, this is a X drink, non-drink, occasional drink. We couldn't get rid of that, despite Richard's effort to get rid of confounding, reverse cause still there. So I think the only thing to answer that question is this causal? If you want to answer reliably, it's by doing randomized control trial, which may not be feasible or even controversial. So another thing we can do is modern epidemiology, is to bring together genetics, which can be done quite nicely in Chinese, because Chinese, like me, we carry flashy gene. We cannot tolerate alcohol. With a one base pair change in these 2 genes, ALDH and ADH from G to A allele, and we greatly reduce alcohol tolerability. So of the 9 possible genotypes, we see over 50-fold in the variations in alcohol consumption. So we can use that, no confounding, no reverse causality. We can actually test whether this is causal. Unfortunately, for today's event, it's not convenient to show the results because I don't want to spoil Richard's reception, dinner, and a drink. So I'll probably just show this one. So we've been working complete flat out. So all the secrets are this file Richard sent. What I'm sure is this one. Look at the time. This is almost 4 a.m. in the morning. He sent to I already went to sleep. It was too late for me, but Richard's still working at 3 a.m. in the morning. Maybe after reception drink, Richard can give a talk about alcohol findings, and so I'm not going to show that. So, very last slide, I just like to acknowledge the members of Richard's extended family in China. It's been 30 years and many generations. And now we've got 4th generations joining us. So this is Richard. The first study, Richard started with Chen Zhensi, Colin Campbell Ecologic Service to big monograph. And this is Madeleine Chen. Sadly, she died aged 91 just a few weeks ago, giving Richard a professorship well before the Oxford. So And this is another big celebration when Richard received a very prestigious award, and with many other colleagues, Liu Boqi, Liu Silu, they all been Yang Gonghuan working together many decades on tobacco. So this is a Richard lecture, and this is time I remember we tried to sort out the permission and the China CDC. And this is the best way now to get Richard working on papers, because he's busy helping others. The time either early evening, early morning, or get him onto the train. Now the journey in China very pleasant. You got bullet trains, very comfortable. This is when I remember we're working for finalizing tobacco paper. So this is Professor Li, the co-lead PR China tobacco, the Kadori Baiban, Li Xing. Many of them cannot be with us today, but they send their best wishes and also have a small presentation maybe towards the end of the session. So the family is growing, and there will be grandchildren and years. And personally, I'm very grateful to Richard for for teaching me not only epidemiology, but also statistics, astronomy, and for many sleepless nights while not working on epidemiology, but also trying to translate Chinese poem into English. It's still a lot of things not done perfectly. I want to continue. I really treasure this journey. It's incredible, and that will remember that for the rest of my life. Thank you very much.
Thanks very much, Zhenming. Now, the next speaker can't say that they've known Richard so long. We're moving back to a student, Dylan Morris, who's talking about blood glucose, diabetes, and aortic aneurysm, followed by not so bleeding obvious, but well, maybe the obvious will hit Richard at some point during your talk.
Okay, thanks, Val, and thanks, Richard, for leading me onto a lifelong epidemiological journey. So in epidemiology, we study the bleeding obvious, the things that really cause big numbers of deaths worldwide. Here in Oxford, we often study things that we know are hazardous, but we really want to know in detail the complete hazards of those risk factors and their effects in very different populations. Very occasionally, we study things that we think are bleedingly obvious, but we end up finding something completely unexpected. And I'm just going to give one example here. So let's take 2 million US adults who are otherwise healthy, and they've referred themselves for vascular screening between 2008 and 2012. They haven't been told to have any sort of screening by any medical professionals, but just for whatever reason, they've decided themselves that they wanted to have their arteries checked for disease. Well, let's study the bleeding obvious. What's the association between diabetes and vascular disease? And if you don't yet have diabetes, does high blood glucose increase your risk of vascular disease? So these 2 million people were asked, yes or no, do you have diabetes? And about 1/5 had blood glucose measurements, mostly fasting. They were screened for vascular disease with ultrasound, including carotid stenosis. That's a narrowing of the arteries in the neck. Peripheral artery disease, blocked arteries in the legs. And also abdominal aortic aneurysm, a ballooning or dilatation of that large artery at the back of the abdomen. Okay, so what's the association of blood glucose, diabetes, and screen-detected vascular disease? Let's start with carotid artery disease. So the black boxes are people without diabetes, white boxes people with diabetes. So if you look first at the non-diabetics, the black boxes, we see that higher blood glucose is associated with higher risk of carotid stenosis. If you have diabetes, your risk is even higher. Well, peripheral artery disease, again, among people without diabetes, higher blood glucose equates to higher risk of lower limb arterial disease. And those with diabetes have about double the risk of people without diabetes with very good blood glucose control. Very consistent with carotid stenosis. Okay, so now abdominal aortic aneurysm. Just starting with, again, people without diabetes, higher blood glucose correlates with higher risk of AAA. Well, what about people with diabetes? Well, they're all the way down there. So if you don't have diabetes, your risk of AAA goes up with higher blood glucose. But then if you have diabetes, then your risk of AAA is then very low. In fact, it's as low as those people without diabetes who have better blood glucose control than I do. So diabetes increases risk of screen-detected carotid stenosis and peripheral artery disease by about 70%. But it's just negatively associated with AAA. That's completely in the opposite direction. Why is this? Could it be that some effect of high blood glucose levels protect the aortic wall against aneurysms? Well, if that was the case, then we'd expect people without diabetes with high glucose to have lower risk of aneurysms. Is it perhaps some sort of confounding? Well, we've adjusted these for the usual confounders in BMI, and we've also looked at smoking, cardiovascular medications, even CRP, and we just can't adjust this out using classical statistical adjusting. Well, is it some sort of selection bias or detection bias? Well, actually, the associations for carotid stenosis and lower limb arterial disease are highly consistent with what we see in previous studies. High blood glucose and diabetes increase your risk. So in summary, if you don't have diabetes, blood glucose is positively associated with atherosclerosis and aneurysms. Diabetes, on the other hand, is positively associated with atherosclerosis, but negatively associated with abdominal aortic aneurysm. And the question I'll put to you is, could some anti-diabetic drug, such as metformin or sulfonylureas, potentially protect against abdominal aortic aneurysm? Study big causes of big diseases in 2 million people, and very occasionally something completely unexpected comes out. And Richard, I couldn't give a talk here today without showing a figure on smoking. We focus very much on vascular disease above the abdomen, but just look how large these hazards are of smoking on leg artery disease and abdominal aortic aneurysm. Thanks.
Thanks, Dylan. Something to think about. Now, the next is Julian Peto, who's going to talk about multi-stage models of cancer, answer to a maiden's prayer. Very intriguing. Now, I guess Julian's not going to start off by saying how long he's known Richard, but maybe you will.
I could. I don't remember meeting Richard very well because I was naught and he was 2. But our mother did tell us later that...
Microphone.
Sorry? Microphone. Microphone? Is it on?
Yeah.
It is on. But our mother told us many years later that when I was about 3 or 4 weeks old, she caught him levering a paving slab into my pram. So it's a good job I don't remember it. But I'm very glad that Val gave the introduction she did. But, I want to talk about a bit more about what we started talking about. How does this work? I mean, following the absolutely seminal paper that Peter Armitage and Richard Doll wrote in 1954, outlining the multi-stage model of cancer, Richard, who joined Richard Doll in 1967, spent a lot of the next 10 years looking at it quite hard to see what could actually be inferred from it. It was a wonderful airy-fairy model, but did it actually give you any solid information about carcinogenesis, about what stem cells do, about what carcinogens do, how to prevent cancer, so on and so forth. And he wrote this paper, and as Val mentioned, I mean, there's a collection of scientists who feel very strongly, as in fact I do, that this really ought to be better known. Now, luckily, it was published in an obscure book, but it was republished in the International Journal of Epidemiology in 2016. And I really do recommend that people read it. I mean, it's a classic piece of scientific writing, and it's, I think, virtually as relevant now as it is then. It's like reading The Origin of the Species. I mean, you know, we know all sorts of things that Darwin didn't know, but he was dead right about everything. And this falls into the same sort of category. I mean, Popper said that the origin of the species wasn't actually, the evolution wasn't a scientific theory because it couldn't be wrong. And I mean, maybe this falls into that category as well, but you can judge for yourselves. Now, I mean, there's a great deal to it, and I can't begin to go through it all. I just wanted to pick out a couple of things. The fundamental idea, which Richard Doll had written on, I mean, particularly a classic paper that he wrote in 1970 or 71, saying that basically aging is cancer. The reason old people get cancer is because the individual cell that's going to take the damage, but the rate of damage is independent of age. And then the core idea that the progression from a normal cell to the pre-cancer, the stage before cancer, involves multiple steps, some of which are accelerated by carcinogens in some cases. And the last one is particularly relevant to what I want to talk about, which is that the pre-cancer, the stage before the cancer, these mysterious cells which just require one further step to become a cancer cell, and we don't actually know what that step is, but we're pretty sure it's not driven by mutagens, because when you stop smoking, your lung cancer rate doesn't drop. It goes up as the fourth power of how long you've been smoking for. And I mean, Richard's analysis of the doctor's smoking cohort was the best data set there ever has been, or ever will be probably, on very precise measurement on exactly who smoked how much and when they stopped. But when you stop smoking, your lung cancer rate essentially freezes. It might go up or down a bit, but I mean, it essentially freezes. And what that suggests is that this pre-cancerous stage, which has been produced by smoking through a multi-stage process, those cells just sit there for the rest of your life, turning into cancer at a constant rate. And what that is, I mean, what on earth is that final step? I mean, there are some quite interesting questions about how cancer works, which I don't think that the people who work on carcinogenesis are all thinking about as much as they should. And the only people who are really thinking about it, I think, are the stem cell biologists. It's not affected by carcinogens. Therefore, this is a key point, the cancer incidence rate is proportional to the prevalence of pre-cancer in the population, or the number of pre-cancer cells you've got in you. So if you're a smoker, you've got a certain number of pre-cancer cells, and that determines your risk of getting lung cancer is just proportional to that number of the cells. Richard did a very nice experiment in the early 1970s where they painted mice with benzpyrene starting at age 10, 25, 40, and 55 weeks. And on the left-hand side, you can see that the cancer rate goes up, starts going up first in the people who painted the mice, the mice who were painted earliest, and so on and so forth. But when you plot the data by time since beginning exposure, they're all exactly the same. So it's a very elegant, direct demonstration of the fact that aging itself has nothing to do with it. It's just how long carcinogenesis has been going on for. Now, these ideas, and the ideas in Richard's 1977 paper, or 76, whatever it was, which you must read. Okay, I mean, ask me afterwards for the reference if you didn't write it down, International Journal of Epidemiology, 2016. Those ideas had a big influence on a lot of people who worked with Richard Dollar. Malcolm Pike wrote a thing in Nature in 1983 about, sort of the extension of it to describe the effect of hormonal changes and explain the age distribution of breast cancer and so on and so forth. I mean, a few years later, I got hold of the mesothelioma data in the American Installation work. It was a huge set, 175 mesotheliomas. And of course, the first thing I did with them was plot this graph, and it's exactly the same. I mean, they're people who first exposed to asbestos at age 20, 30, 40. The people exposed at age 40, they die of old age before they have time to get mesothelioma. But if you plot them by time since first asbestos exposure, the curves are absolutely identical. And so it's informed the way people have looked at both, practical questions like this and theoretical questions about how cancer works ever since. Now, we come to the Maiden's Prayer. I mean, this is, Richard lost interest in all this in about 1977. I remember him saying to me that he'd been doing cancer research for 10 years and he didn't think he'd saved a single life. So he's going to change direction. And this meeting has essentially been entirely devoted to what he did after he changed direction in 1977. So I'm talking about what he did before 1977. And it really was seminal. But it's still relevant. And so now I want to talk about what I've been doing for the last 2 or 3 months. The problem with cervical cancer is that it's all caused by HPV, the human papillomavirus, which is sexually transmitted, hence the Maiden's Prayer. Most women have been infected. I mean, well over 50% of women have been infected, and most of them were infected before the age of 25. And an infection is a lot rarer after 1945, after age 45 or 50, for obvious reasons. And so what we know about it is that The screening age was raised from 20 to 25 in 2004 because screening at age 20 was thought to be ineffective. And that has, in fact, and the latest data, just the data from 2016, you got a whole sort of 5 years, and the cancer rate has increased quite substantially in women aged 25 to 29 who were born after 2004 as a result of it. We need to understand why that was. I mean, it's no longer very relevant because of HPV vaccination. The vaccinated cohort are just beginning screening, so the risks are going to be much lower. But I mean, most of the world hasn't been vaccinated. I mean, all the women who were born before 1991 weren't vaccinated. And on top of everything else, we're now changing over from cytology to HPV testing. It's actually replacing cytology at the moment, and it'll be complete by the end of next year. So we're replacing cytology with screening. We don't understand how cytology works, and we've got no idea how to do HPV screening, what age you should do it from, how often you should do it, and so on. So it's quite an important question. So, the multi-stage knight to the maiden's rescue. This is the age distribution of cervical cancer in unscreened populations. These are actually death rates in Britain in people born in about 1920. Screening was introduced very suddenly in 1988 in Britain. That's a key fact in what I'm going to say. And so from 1988 onwards, all women in Britain over the age of 20 were invited every 3 or 5 years for screening, and most of them attended. So we went basically from no screening to universal screening very abruptly. But this is what happens with no screening. The cancer rate is zero below age 20. It's tiny at 20 to 24. It's creeping up at 25 to 29. And then it goes up very, very steeply to about 40 to 44. But then it flattens off. And from age 50 onwards, right up to age 80, in fact, it's as flat as a pancake. It just doesn't change at all. Now, of course, what the multi-stage model says is that the fundamental assumption is that cervical cancer incidence is proportional to the prevalence of cervical pre-cancer in the population. So this is you know, how many people have got cervical pre-cancer in the population. And not surprisingly, it goes up incredibly steeply with HPV infection during the period when HPV infection is common, up to the age of 30 or 35. As HPV infection becomes rarer, it flattens out, and when there's no more HPV infection, it stays where it is. So screening is aiming to detect pre-cancer and treat it. That's what cervical screening does. Now, we want a mathematical model to describe this. That's what statisticians like. So I must mention the effect of screening. This is what happened after 1988. These are people born, these are women born in about 1933, who were 55 in 1988 when screening started. So their cervical cancer rate goes up until they're 55, but then drops. Remember that they stayed constant in unscreened populations, which incidentally is seen in every developing country in the world. If you look at within birth cohorts, in unscreened populations, you get the same pattern of going up to age 45 and they're just flattening off. These people are born in 1933. These people were born in 1943. So they're screened from age 45, and their rate goes up to age 45 and then drops when they start screening. And these people are born in 1953, you get the same thing. So the effect of screening is to detect pre-cancer and treat it, and therefore reduce the cancer rate. Lovely. But we want to quantify that. So what's the best model? Well, the simplest possible model that's consistent with what we know is that every new HPV infection has a constant probability, averaged across HPV types. I mean, some are worse than others, but I mean, on average, a new HPV infection has a fixed probability of causing a pre-cancer, SIN3 or carcinoma in situ, whatever you want to call it. We know the age distribution of HPV infection because we've done big studies, and we get people who haven't got HPV and ask them if they've got HPV. We did ask them, actually, we take a sample 3 years later and see how many of them got it. So we know the age distribution of new HPV infection. So we know the age distribution of pre-cancer. Now, pre-cancer progresses to cervical cancer at a constant rate, the fundamental multi-stage assumption. And the other thing you have to put in the model is the lag. There's a 7 or 8 year lag from HPV infection to the first diagnosis of the cancer it causes. And we know it's more than 5 years. I mean, plenty of people get HPV when they're 14 or 15, and nobody ever gets cervical cancer before they're 20. One of the 2,600 cases in 2016 was aged under 20. But it's quite common by the age of 25. So we know it's somewhere between 5 and 10 years, so say 7.5 years, from HPV infection to the manifestation of cancer. And we then got to put screening in. Well, I mean, it reduces it by a certain proportion every time you're screened. And it turns out, surprisingly, that the best estimate is 40%. But anyway, so there's only 2 parameters in the model. There's the 7.5-year lag from getting infected to any effect on cancer, and 40% of SYN3s are detected every time you screen. And when you push the button on this and fit it to national cohorts, people born in 1958 were screened from age 30. People born in 1968 from age 20, 78 from age 20, but 88, the screening age was raised to 25. And the prediction, the orange line is the model and the blue line is the data. But the correspondence between this trivially simple model and what's actually happened is absolutely spectacular. And because it's so, the fit is so good, and because it's so biologically plausible, thanks to what Richard wrote in 1976, I think it's true. And I think this is the basis for deciding how to screen. It would certainly have prevented us from raising the screening age from 20 to 25 on the basis it wasn't going to do anything to cancer. And so the inferences we can draw is that cervical pre-cancer is cytologically normal more than half the time. You only pick up 40% of them every time you screen, which is very surprising and offensive to most people who actually spend their days looking through colposcopes, because they define SYN3 as a severe dysplasia that penetrates the epithelium. So obviously it's visible. But what this very strongly suggests is that that's not true, that it's there in the basal layer, it's causing cancer, but it's not manifest on a smear, and it's not manifest to a colposcopist. So now we understand why raising the screening age from 20 to 25 increased the cancer rate. And most important of all in the modern context is we now know how to do HPV screening, or at least we've got a framework within which to decide how to do it. We know what's going on, we know what the aim of screening is, and we know what to measure to decide how to do the screening. And so the answer to the maiden's prayer, in a sense, all that doesn't much matter in Britain. I mean, the number of cervical cancer tests has dropped now below 1,000 a year, and it's still dropping. And with the advent of HPV screening, however well or badly it does, it'll do even better. But it's a major problem in the developing world. I mean, it's the second commonest cancer in women after breast cancer in the developing world. And there's 500,000 cases a year and 250,000. And I can't compete with Richard, but I mean, 250,000 deaths a year is not bad. And 80% of them are after age 45. And what this model strongly suggests, and is pretty obvious anyway, is that virtually all of those are caused by pre-cancer, which is there at age 45. So if you give one test at age 45, a sensitive HPV test, you'll detect the whole lot. Now the question is what you then do. I mean, in Britain, we recall women every 5 years until something happened or nothing happened, and a whole lot of them would get cancer while we were doing it. But in fact, the effect of cervical, the only serious contraindication to cervical ablation in a postmenopausal woman is the risk of premature delivery, which is 0. So if you test all postmenopausal women with a sensitive HPV test and treat the whole lot, you can eradicate most of those 80% of cervical cancers, which is 200,000 deaths a year in the world. As I said, I can't compete with Richard, it's not bad going. But it's all thanks to his model, which he wrote in 1976. And as I say, he said he was giving it up. He said he'd spent 10 years doing that, not saved a life, so he was going to do something else. But I mean, there's still something in what the old dog said 41 years ago. Thank you.
Thanks very much, Julian. Now, John Dinesh is going to talk to us, and his title is Emerging from the Shadows. John was Richard's PhD student some years ago. I'm sure he'll tell us.
Yes, so actually, Richard and Rory's PhD student. And the topic of my thesis was, can you catch a heart attack? I spent 4 years coming to the conclusion that the way to a man or woman's heart is probably not through their stomach. That Helicobacter pylori was not likely to be a causal etiological factor in coronary disease. But what I learned from that about the need to study at scale for systematic approaches and to try to mix biology with epidemiology is something which has persisted, and that's what I'd like to discuss today. Chronic infections and heart disease was a fever of the mid-1990s. One of our current areas of intense interest is this idea of multiomics. And essentially this talk is to say that assay technologies seem to be finally catching up with Richard Pito's vision for large-scale blood-based epidemiology. And it's much easier nowadays to make the argument for such studies, largely because finally, after 30, 40 years that Richard's been making the points, the technologies are maturing. So we now have a language to talk about these technologies. We call them omics, to refer to collectivities. The collection of the human genome we call genomics. And therefore, by analogy, the collection of proteins we call proteomics, lipidomics. Someone once said the only omics that really matters is economics, because these things are expensive. What they share in common is that in contrast with static DNA, these are dynamic, potentially modifiable factors. And therefore, the hope is that they may lead to some breakthroughs in understanding, perhaps identifying a new LDL cholesterol, or tell us about the mechanistic chain of events that link DNA genetic variation with disease. We've been very good at building DNA maps in the last 20 years, but these maps are somewhat barren. They're not actionable maps because we cannot connect the DNA letters with the diseases through any kind of meaningful knowledge. And that's the quest of this type of endeavor. So these are the types of areas that have been trumpeted as potentially valuable. And of course, the idea is to try to tackle this with some of the inherent skepticism of an epidemiologist and to use Pito's paradigm. Is it really worthwhile, then it's worth doing well or worth doing reliably. So these are some of the things that we really don't know about some of these assay technologies. We don't know really their basic properties, how well they work in populations. They may measure many things, but are they measuring things that are meaningful, reproducible? And I'd like to show you a few slides that suggest that at least for a few of these technologies, we may be making some surprising progress. So in Cambridge, I lead a program, systems genomics programs, if you like, that's trying to combine some of these assays in the same individuals who have been sequenced and linked with health records. And today I'm just going to tell you about the study of proteins. Proteins fulfill the bleeding obvious paradigm. They're the building blocks of biology. When they go wrong, diseases happen, and they're the targets of many drugs. So they seem a natural place to start. And the reason why it's been very difficult to study them at scale, both in lots of people and lots of proteins, is that proteins are a many-splendored thing. So for example, this assay system measures 5,000 proteins, and one of the key things that was difficult that it achieved that others haven't done is that proteins exist over 8 orders of magnitude, so many different, almost a billion-fold different concentrations in the blood. So coming up with an assay system that measures the most minute proteins as well as the really common ones is tricky. This inventive company has come up with these so-called aptamers, single strands of DNA, and they combine, a bit like Richard, both analog and digital properties. So they're analog because they can wrap themselves around proteins, and they're digital because they can hybridize with other strands of DNA. So you get reasonably specific reads of many different proteins in a quantitative way, at least in relative quantities. It's not quite an agnostic platform. As you can see in this case, the proteins have been selected because of known biology and potential therapeutic target interest. So over the last couple years, we've tried to evaluate this assay system, and the results came out last month, led by PhD student Ben Sun in my group, and also principally led by Adam Butterworth. So what I'd like to show you is how we took some of the basic principles of epidemiology that Richard Pito has taught us and try to apply that to an assay system that measures several thousand proteins concurrently. The first question is, are the assays reproducible within an assay plate? And the answer is that for most of these proteins, the coefficients of variation are reasonable. The second question is the concept of regression dilution that Sarah Lewington introduced. What is the year-to-year chopping and changing within individuals of these proteins? And as you can see here, there is a distribution, but many of the proteins fall in this 0.4 to 0.7 range, which is comparable to risk factors that we understand well, like blood pressure or LDL cholesterol. So there are, for the large majority, meaningful results. do these proteins correlate with known features of physiology or epidemiology? And the answer is, for those that we have good examples, the answer is yes. And then perhaps the type of validation that makes us even more satisfied is this. So let me explain this somewhat complicated slide. Each dot that you're seeing is a highly significant statistical association that connects one letter of the genome with one of the proteins, one of the 3,500 proteins measured by this system. So if you look at the horizontal axis, this is ordered by the genome. So these are the chromosomes, 1 to 22. And then the vertical axis takes advantage of the unique property of DNA that each protein, each gene encodes one protein. So we've numbered the proteins that are encoded by the same genes in the same order. And so this beautiful red diagonal line is telling us that we're finding many hundreds of examples where the gene, a variant that's in or near a gene, encodes its own protein. And of course, this is a validation that the assay system is working. The blue verticals tell us something interesting. They tell us about hubs of protein machinery. So some of these hubs are already well known, complement factor H. So for example, responsible for many biological cascades, protein cascades. Other ones are perhaps more surprising. And then the side-to-side scatter tells us perhaps potentially about new biology, associations between proteins and protein systems that weren't known before. And one of the potential advantages of this type of approach is that it may help tell us something about etiological factors in disease. So here's one example. It's an enzyme that's produced by a white cell called a macrophage. It's called MMP12. It's a bit of a mouthful. But it's under investigation in certain pharmaceutical companies as a possible inhibitors to it as a way of treating chronic lung disease. One of the findings from this protein assay is that we're able to build these types of allelic scores where we can look at, across a gene, many different independent variants to try to create something of a genetic mimic of drug effects. So in this case, we can explain about 15% of the variation in blood levels of this enzyme with about 12 or 15 independent genetic variants. And this works a bit like a dimmer switch. So these genetic variants are associated with lowering, with higher levels, these with lower levels. And then when we project this information into separate samples of cardiovascular disease using something that Zheng Ming alluded to before, a technique called Mendelian randomization analysis, we see this surprising result that higher levels seem to be protective of disease. And we see this not only for coronary disease, but we see it for stroke, suggesting that those companies that are developing inhibitors to these agents might want to be careful. So as a vignette. So Valerie's asked me to stop, so I think I'll stop there by basically saying that assay technology is finally catching up with Richard Pito's vision, and I've been very lucky to have excellent PhD supervisors. Thank you very much.
Thanks, John. Just as any modern scientific symposium, there's always some late-breaking event. And so I'm just going to turn it over to Zhenming and his colleagues for something that's not programmed. While they're coming onto the stage, we'll postpone the next session to start at 4 o'clock rather than now.
Cannot join us. So instead, the prepared subsidy to present Richard and thanks Richard for the inspiration, collaboration, and so this is a small souvenir from China. So all the new members of Richard's
Photoshop collaborators in front of the temple. Thank you to all the previous speakers and possibly any subsequent ones.
Okay, time to be quiet. We're ready to start the last session. Okay, before we start it, Mike Gaziano is going to arrange a gift.
Yes, so I'm going to give Sir Richard a token of appreciation from the Harvard group. We are also in the diaspora, and we thought we had a special way of really realizing that it's a global diaspora. I am in the lineage, as my mentor, and as a token of appreciation and a token of talent, this is a limited edition position also high. We gave out to the positions for the 20th anniversary. We're now at the 50th anniversary, so we saved three. We have many people saying it's a wonderful gift, and I have a few bits of hate mail saying how she spends valuable NIH dollars on something. But the most poignant one was the moment that we had a fellow say that his father was so proud of me, and let's say when he passed away, he knew he sent his medical record, that his father requested to be buried in his position called full-time. Helping us develop our population science both on the other.
You've got to say something bad as well. Come on.
Well, this is something.
This is Richard Dole's one. I'm taking up for
And if I'm giving you your retirement quote, I'm sure you're going to be spending all the time in your traditional areas of research. I'm going to give you something truly important, a truly important statistical problem, which is there's no sport with greater statistical analysis in baseball. The major league. So you can help us figure out statistics of a left-handed batter on Tuesday during a day game.
I went to one Boston Red Sox game, Charlie took me, and somebody hit the ball over the edge, and for some reason the crowd were ready piece of the ball to be hit over the edge and out of the ground, so they all started crowding going. And all of them shouting and I looked around, there were about 35,000 people there. In the middle of Boston, there was not one single black face. There was entirely white. So anyway,
Okay, we're about to start section 3 called Moderate Treatment Effects Matter, and I'm going to give just a brief introduction, and I regret it, but I didn't make any slides, so you got to bear with me. See if I can actually read this. I should note that getting here was not easy from the United States, but it's a real pleasure to be here at the celebration of such an important person. As part of getting ready, I scanned some of the literature, which is so easy to do nowadays, and noted a few things that are interesting, at least in part because they're so in sync with current interest. I don't know how much this has come here, but the United States is obsessed with real-world data, by which they mean not clear what they mean. But many of the things that Richard was pushing are closely related to that. Simplifying the conduct of trials, not collecting data that doesn't really matter that much, applying broad inclusion criteria, everybody's for that. And of course you really do want to know about all people and even people on other drugs and people with milder disease. You do want to know all that. Seeking modest but still critical effects. After all, you get 50% reductions in some things in oncology or in something, but in cardiovascular medicine, it's a good day if you get a 10% reduction in mortality. And he also made use of meta-analyses to try to figure out how to design the studies. All of these are very much on people's mind. The interest in dealing with subgroups is also a matter of great interest, and it's worth noting that in many of the trials that Richard was part of, there was plenty of subgroup looking. He just wanted you to be cautious about believing it too much. Anyway, in ISIS-2, for example, which I looked up, there were all kinds of modern things. It was a factorial study. We don't see nearly enough of those, but you really do want to know how and whether drugs interact. It looked closely at effects over time and looked at the effect of when you started the treatment, very important. And it looked at those subgroups, the subgroups that were defined by when you started the therapy. And there were some important findings, not as much as some people had thought there were going to be. And it was big enough to assess mortality, which a lot of trials these days don't do, because the trial would have to have 18,000 people in it, and they don't want to do that. And then, of course, although it presented 50 or 60 subgroups, I have the paper with me, it also presented the most famous subgroup rebuttal ever, the astrological signs. Whereas people in certain signs had no effect and the other people did have an effect. That was not to assert that that was true. It was to assert that subgroups can be ridiculous and you should be very careful. It's probably the most quoted subgroup rebuttal I've ever been aware of. That's not to say that sometimes you don't find important subgroups. At least ones that we as FDA have believed. We believe that Bidil works in blacks, but not particularly well in whites. There's 2 good VA studies that show that, and the label indicates it only for the black population. The antiplatelet drug ticagrelor, given in people after a heart attack, didn't work at all in the US compared to clopidogrel. It was inferior, but it was superior everywhere else. We eventually decided that was because high doses of aspirin were used in the United States. So the subgroup effect, made us feel good. So they're not never, you just have to be cautious. Anyway, it is worth saying how much what he did so many years ago fits with current interest. ISIS was a trial that was done in a real-world environment using information that's ordinarily collected, death and stuff like that. It was done largely in the healthcare system. It was not very disruptive. And it got at the critical measures, but not the others, many of which were collected in the course of healthcare. So there is a strong movement to see if people can do trials more readily. What the conflict is that a lot of people who offer this kind of hope want to use epidemiologic studies, but of course, Richard's studies were still rigorous and randomized, and that's what we all hope. I wanted to make one last pitch. And that is, there was a lot of discussion about how we're not doing as well on treating certain diseases as others. And one of my obsessions, but without any effect on anybody to date, is finding out why people stop therapy. The last figures I saw say that 50% of people started on an antihypertensive are no longer on it at the end of a year. There have been some improvements in some places. Cleveland Clinic tried to mediate that. And you see similar reports of people starting statins, that half of them are off them by the end of a year. That, to me, is probably the major public health problem in the United States. These are all treatments that have profound effects on survival and other consequences. And I think there ought to be active research on how to make people stay on it, whether it's giving them lottery tickets or obsessing them or having their wives yell at them. I don't know. But there are very few controlled trials on this. So that's my pitch for an area that people ought to be more interested in. Okay, with that, let me introduce Mike Brown. Oh, this is a video. It's on cholesterol lowering, so do I have to do anything to get the video going? No.
I'm delighted to have this opportunity.
Okay, Larry Norton is next.
Okay. Hey, how are you?
Hey.
That's good. A great pleasure to be here. I'm a breast cancer doctor. Would every other breast cancer doctor in the room raise your hand? Yeah, that's what I thought. I'm from Memorial Sloan Kettering Cancer Center in New York. I do a lot of jobs, but what I'm here mostly to talk about is the Early Breast Cancer Trials Collaborative Group. It's a collaboration that started, I think, mid-'80s. I got involved in it at least in the mid-'80s. And it was revolutionary and continues to be revolutionary. We just finished our meeting here in Oxford, 2.5-day meeting just earlier this week, and still making important discoveries. It's based on the idea of meta-analysis, and it's because in the treatment of breast cancer, there have been historically a lot of small studies, and sometimes those studies seem to be conclusive, sometimes they're misleading. But nevertheless, big questions such as what's the right surgery? Does the kind of surgery matter? If you have breast conserving surgery, does radiation to the breast matter? Two means of, in the adjuvant setting, that is after surgery or sometimes before surgery, using medicinal therapy to prevent recurrence of disease, endocrine treatments for estrogen receptor positive disease, chemotherapy, which kills cells whether the cells are estrogen receptor positive or not. Major questions in the very beginning, do any of these things make a difference? Is the type of chemotherapy, does that make a difference? The drugs that are used, combination chemotherapy, then much more subtle issues. And over the years, these have been addressed by the meta-analysis of all the big ones. And I think that this is probably one of the great management, not just of Richard Pito and of this activity and of his colleagues. Partially because you'll notice if you spend some time reading the book, which is an icon of iconoclasm. An icon is not a god, an icon is a symbol. And it's a very important philosophical concept that all of us as humans need symbols to think by. You can't think in all the details all the time, or your mind is cluttered up with a lot of noise. You have to have some way of summarizing complex data sets, complex ideas, and that's what symbols or signs do. And this has been a fundamental principle of philosophy for many, many years, including this important quote: "We have no power of thinking without signs," which means symbols. So I would actually like to focus in on this universal symbol, which is the Tai Chi, which is the yin-yang Asian symbol, commonly referred to as the concept of you need opposites to interact to make wholes. It has many other meanings, and I would like to talk about this. And I'd like to talk about how symbols sometimes simplify complex systems and how symbols sometimes confuse us and lead us astray. But I'd like to bring this into the context of another symbol, which is a revolution in art that happened in the 1960s. This is the work of Sol LeWitt, great American artist, and it was the era in the 1960s of conceptual art. The concept being, it's not the object, it's the concept of the object that really is the art form. And you know, if somebody actually broke into the Louvre and destroyed the Mona Lisa, there's enough copies out there, enough people have seen it, enough been written about it, it would still be the greatest work of art, or one of the greatest works of art of all time, whether the object actually exists or not. It's the idea of that painting that really is the essential of the art. This was the revolution of the 60s. Both Richard and I are children of the 60s, and I think this was very influential in my thinking, and I think is representative of, in overview of his impact in the field and why he's had such an impact. Because the era of conceptualization in breast cancer management started with single observations. A patient with an estrogen receptor positive breast cancer, if you do something to interfere with the biological function of the estrogen receptor, that patient with advanced breast cancer, that tumor will shrink. And then the question arises, well, what if we give these drugs earlier on, let's say right at the time of surgery, where there might be micrometastatic disease, spread of cancer cells throughout the body that we actually can't see. And so small groups of patients were treated, and there was a suggestion that there was a benefit in that regard. The number of observations grows, and eventually something really remarkable happens, which is the invention of the system of prospective randomized controlled trials. The idea of doing things where patients are randomized and allocated in a random fashion to one treatment or another, and then a comparison. And this is kind of where I got into the field. In particular, I was associated with one group of hospitals working together to answer these questions, the Cancer and Leukemia Group B, and we had done trials, and we had great belief in those trials. And then along came this guy, Richard Pito, who says, well, you know, you may have confidence in your trials, but that's a form of tribalism. You believe it because you did it, because your friends did it, and it may or may not be true, because even though you dealt with thousands of patients, it may not be representative of the entire universe of patients. And so I was very upset by this, and I thought this was a great challenge. It was certainly a challenge to my ego and the ego of all my colleagues, and I was actually rather resistant of the idea that I actually had to combine my data with other data sets to be able to derive some truth, because I knew what the truth was. The truth is what I did and the observations that I made. And I am not the only person who stood up here today and said that my relationship with this man, which has now lasted more than 30 years, was born in contentiousness. It seems to be a common pattern, Sir Richard, you know. But when you're arguing with somebody actually with such intelligence and such dedication and such high moral values, such integrity, you say you've got to pay attention to this. And so I started coming to the meetings. And when I started coming to the meetings, I saw that I was really totally wrong, is that there is a tremendous value in doing large studies and even greater value in being able to group these studies in such a way that with statistical elegance you can derive truths that may not be apparent within each individual study. And slowly the entire community of breast cancer doctors, breast cancer investigative doctors really saw the wisdom of this particular approach and learned fundamental truths that could not be obtained by any other means. Now, Richard goes to great pains to say that he didn't invent the concept of the overview, but I did think he perfected it, at least for cancer, all right? And partially because of the methodology. And short talk, we can't go into those details, but partially because of the graphic representation. As you've seen many of the graphs that have been presented here as well. The forest plots, for example, is a way of actually looking at the data and making it conceptual. And looking at life table results, which I'm going to show you in a second. It's my only data slide that I'm going to show next. And this has been reproduced really throughout the entire community of cancer doctors in terms of the ways they look at the data, because visualization is a very, very powerful tool, and it is a form of iconography. It's a symbol of very, very complex data sets, but it's a symbol that really conveys a very, very important message. The one study I'll show you is one that I was very involved in, and just giving you a little bit of history, I think, not necessarily to emphasize my own involvement, but to emphasize why this is such an important and revolutionary way of looking at data. I had an idea when I was very young, you know, basically it's more than 40 years ago, published the first paper, that the way we were giving chemotherapy was not ideal and we should make certain modifications. Details not important. It's called dose density, squeezing the drugs closer together and also giving them in a sequential fashion, which also accomplishes a form of density. It's a whole 45-minute talk and it's not germane. The point is that we did some studies and other people did studies, and eventually there were more than 20 high-quality studies. 25 actually went into this particular analysis, and they didn't all come into the same conclusion, although they largely moved off in the same direction. And this was just recently done, and recently and soon to be published, but this was presented at the big breast cancer meeting that we have in San Antonio, Texas every year around Christmas time, showing that among 34,000 patients female patients who were randomized, that the application of that idea of the better way of using drugs has a big influence on the recurrence of disease and on breast cancer death rates, and does not have an overall impact at all on death from other causes, so it's not incrementally toxic, and indeed all-cause mortality is reduced. Right now, in the United States, where a lot of these ideas were born, at its peak, about 60% of patients who were candidates for dose-dense therapy were getting it. It then started to fall, and it now is in the range of about 25% of patients getting this therapy. No incremental toxicity, reduction in all-cause mortality. In other parts of the world, it's even lower utilization. Part of the reason is it's based on an idea, it's not based on a drug. If you have a new drug in cancer and the drug seems to work, there's almost immediate acceptance across the board, and the more expensive it is, the more it's accepted, it seems. And that's another issue that we have to wrestle with, really, as a community. But this was an idea. This was a concept. Concepts are hard for people to wrap their brains around. A drug, they can see in a bottle, they know what this does. But because of this analysis, 34,000 randomized patients in 25 trials, the expectation of my community, and we have a very good feel for it because so many of the hundreds of investigators of major importance throughout the world come to the meeting in Oxford that's held every 5 years. We're going to see a dramatic increase in the utilization of the concept and a significant, small but significant drop in the death rates of breast cancer of the patients who are so treated. And this is a very powerful thing. It's more powerful than just having an idea. It's more powerful even than having a drug, is being able to convince a community that this makes sense. And this is the power of the overview concept. Now, part of the reason why this is of special concern to me right now is that we have moved away from the era of the concept. Now we're in the era of the drug. This is because of revolutions in molecular medicine that have identified abnormalities in cancer cells that seem to be associated with the disease. You call them driver mutations, and they could be other abnormalities besides mutations, but driver mutations is a good summary of many of them. And people are convinced that if you find the mutation and you have a drug that can affect mutation, and you can do even one patient where you know the target and you know the drug and the drug works, you're done. It's called N=1 trials. And it's becoming extremely popular now and is just basically flooding the literature. Because of this, and because people have tried to replicate it and it doesn't always work or don't really know why it works, we're seeing a new type of study called basket studies, which are uncontrolled studies where you identify the mutation regardless of the organ that it comes from. So a patient could have stomach cancer or breast cancer or lung cancer, but they have a certain mutation, and you give the drug and a certain percentage of them respond. This is like the early days here. We're here. And this, for the most part, is lacking. And when this occurs, we're seeing a tremendous number of negative small trials. And why negative small trials is of great concern to me, that if you're going to see a moderate effect that could save many, many lives with a common disease like breast cancer, you're going to need large trials. We know this from the era of the concept. To get a good large trial, you got to have an important question. You got to have reliability of your answer, which is associated with size and either a massive large trial or overviews of a number of still large trials. The problem has to be common so that a small effect times a lot of people is going to help a lot of people. You need an intervention that people can actually receive. And I think cost is a very big issue in this regard. You have to know what you're measuring and measure it accurately. Death is obviously a very important variable and something we can measure. And recognize that most of the effects that really are important are not huge. They're moderate. But moderate effects, considering the variability between people and the number of people that can be affected by a common disease, are very important. And actually, Richard wrote about this in a paper at about the time that I started getting involved in the Early Breast Cancer Trials Collaborative Group into the mid-'80s. That was extremely influential in my thinking and still is to this day, which is, and I think his co-authors are well represented in this room, that you can lose a moderate effect if you have the probability of achieving a p-value, a one-sided p-value at 0.01 of significance. If your effect is 25%, can be easily lost even with trials that are measuring in the hundreds, and to get a low error rate, you have to go to large trials or meta-analyses that may mimic, with some loss of power, exactly that effect. I am very concerned that as we have been seduced by precision medicine, and I'm one of the people working in the area, a lot of my research is involved in the area of molecular targeting, is that we are throwing away good drugs because our trials are really too small. Now, so I have real questions about what have we forgotten from the past in terms of abandoning the concept of large trials. When are large trials reasonable? Well, if you expect a huge effect, and that's what their expectation is, and you've got reason to believe a huge effect, you may be able to get away with it. It's easier to do. It may have commercial value or more rapid translation to commercial value, that is economic value for the manufacturer of that product. It certainly will get more papers out quickly, and so you can get promotion. But also there is a tyranny of journals that lean right now in cancer toward those kinds of papers. They're very, very attractive. You know, you do molecular biology, you know your target, you've got a drug, you actually can show that it works, you could actually have that impact. And there's a seductive nature of it which could get us into trouble in cancer medicine unless we remember the concepts of the past. So that if I were going to say overall what the impact of Richard Pito is, organizing this international effort where everybody comes together and everybody works together for a common goal, great impact. Inventing new ways of looking at the data so we have reliable results and that it does indeed influence the way we treat patients, a huge impact. Defining the situations that we need to actually be able to accomplish this, a huge impact. But in my mind, the real impact is the fact that it's bringing conceptual thinking back into the area, and we have to hold on to that conceptual thinking as we move forward. Overall approaches toward the disease by looking at very, very large data sets together. And the idea that it's the concept that's really important and that we have to do trials and meta-analyses to understand those concepts, that's the icon that I think is going to last. Thank you all very much.
Okay, we have another video. Richard Gray. Okay, it's time for Dr. Califf.
Well, today I had a classic pedo interaction. I finally came across the man and I said, "How's it going?" And he said, "Well, I was having a great day until I saw you." And to understand that statement completely, you have to understand that my relatives came over on a prison boat to South Carolina from this part of the world. And I think we keep replaying that for over 20 years every time we see each other, having not quite gotten over it. So I want to join the crowd in saying the best times with Richard Peto when you have a really good argument and you go at it. There's no question about it. But then I want to switch into something I think is very serious. And it's really a ditto to Larry Norton. It's kind of amazing. His talk, I could just sit down, but I'm not going to do that. I'll take my 15 minutes and see if I can convince you that there's a lot at stake right now in adhering to the principle in the face of a radical change that's occurring in the information environment that we're operating in. And the title, many of you will get into this a little bit more. The FDA has had a saying led by Janet Woodcock for a while about certain kinds of trials called SCTs, which actually, the argument about that arose in a meeting where Harold Varmus from NCI, a famous guy, was talking about precision medicine. And Janet Woodcock said, "You know, all those trials you do, they're SCTs." And he thought that was a compliment at first. And then about 5 minutes later, she revealed that meant small, crappy trial. And so what does that really mean? And I come back to the same article. It's quite remarkable. We did not plan this, but we end up with this very influential article that Salim was first author on, and I think was a core part of the lineage that many of us in other parts of the world read and thought about a lot. And I think what's in there is still holding true today. And Larry went through these items. This is my sort of southern interpretation of the first page of that article, which for me has been a guidebook, including my time at the FDA. But this way of thinking is under threat right now for many reasons. And I think there is a way out of it that could be glorious and much more positive, but we'll see what you think. Evidence of the threat came from the revelations now coming from clinicaltrials.gov. I had the privilege of doing a lot of work of getting this around over the years. And the most shocking thing to people when you actually go through it with them is that the vast majority of clinical trials that are done are sort of next to worthless. They couldn't possibly answer a meaningful question. Particularly the academic trials are often so tiny and so inconsequential that they are not even published. It was a shocker to people to see that industry-funded trials were more likely to be published than academically funded trials. And the reason goes back to the basic design. All too often in academia, people do small trials because that's all they can do. The thought of working together to do something larger has been antithetical to the way of life. And the result of that is that despite the wonderful trials and the advances that have been made, for most of the major decisions that we make in a clinic today, we don't know the right answer. We're guessing. And in fact, that number almost precisely in cardiology today is about 80% of the time we don't know what the right thing to do is when we come to a key decision node. And I would put forward that even at its best, the large sample trial, the way it's been done, is too hard to do to get to the point that we really need for the kind of evidence that would really drive clinical practice to a different level. And so I have a nomenclature for clinical trials I've been using, and I plan to write a little bit about this and put them into 4 categories. And I think now the data is getting better and better in clinicaltrials.gov with mandatory results reporting. So you could classify 4 types of trials. Small, crappy trials. I've already described what those are. They're characterized by usually having a nonspecific protocol, no clear hypothesis, inadequate power, and unlikely to ever be published. We do have small, elegant trials, and I bolded some large trials because I do think there's a need for a vibrant set of small, elegant trials that really answer questions to offer up out of the many potential therapies that are proliferating now because of the changes in biology, to have us do the large trials on the best of the breed. Remember that at the FDA, 90% of the drugs that get into phase 1 don't make it onto the market because they have unexpected toxicity or some other problem along the way. Usually, these things can be detected by smaller mechanistic trials, but we need to demand, because these are so labor-intensive and detract from the collaborative behavior that's needed to answer the critical clinical questions, we need to demand a different level of quality for those trials to be done. And then the fourth category is, this is a new one for me, large wasteful trials. And that's almost every industry-funded trial now is doing a whole bunch of stuff that's a total waste of money, with trials costing up to $1 billion per clinical trial being done. And for years, we've been arguing back and forth with Dr. Temple. For a while, I was on the other side of the fence. Is the cause of this the FDA, or is the FDA just a victim of the way the industry deals with the FDA to cause all this to be done? But the result of large wasteful trials is that it's crowding out the best in many areas. And a consequence of the combination of what Larry said and what I'm saying is that the investment now is almost all going into rare diseases and where precision trials are being done. A massive underinvestment in the causes of death and disability. The opportunity, and the reason that I'm spending half my time in Silicon Valley now, I still tell the house staff that the greatest invention for my career in clinical trials was the fax machine. The idea that you could stick something in a machine and it would come out on the other end was totally revolutionary. Most of the 20-year-olds now, they just can't even relate to what the heck are you talking about with that. The fourth industrial revolution is this new place where we are now, the digital revolution, where the sciences are merging into information disciplines in totality. So you think about 3.2 billion base pairs, what John Dinesh talked about today. It's all being distilled into information. And now we have a situation where all of our cell phones connected to the cloud have more computing power than entire universities had just a couple of years ago. And they're not just means of computing, they're means of transmitting information in a bidirectional manner globally without a digital divide. That is, cell phone numbers are higher in lower income people than higher income people now because of the way our societies have evolved. So how do we take advantage of this going forward? And I think there are two ways that we do it. The first is to really demand that when we do small trials, that they are elegant and that they take into account the complexity of biology that we can now measure. And the second is that we radically change the way we think about clinical practice and randomization and large trials. This is my view of where we've been up until now. It's not a new idea. But in my career of mostly finding negative results in phase 3 and beyond trials, it's almost always been because the developers could only look at one part of the elephant, not the entire elephant, and things were happening in some other pathway that hadn't been anticipated. But now we can fuzzily see the entire elephant, and we can see the herd of elephants and the terrain on which they're operating through geospatial analyses, which happen in real time. We had a great time with the Global Burden of Disease group yesterday at Google with the whole universe of Google entities, imagining what could happen if you put all of the geospatial data together with time-oriented data about not just electronic health records, but all of the social information, which is now readily available in the universe of a place like Google. And so we're now beginning to say the big job ahead of us over the next few years is to do what we've done with roads and cars. 10 years ago, if I had told you, you're going to get into your car and you'll start talking to your car. Now, Richard may have talked to his car 10 years ago, I would guess, and your car will talk back to you, And it will change what it says based on what's happening simultaneously on every road in the country that you're in. You probably would have thought I was crazy. But that's happening as a routine, and it's a strange thought now for people to think about pulling off to the side of the road and taking out a map and looking at it to figure out where to go. The reason that can be done is because every road has been mapped and is kept up to date. And yet for human health, we haven't done that exercise. Rory's British Biobank is the leading cutting edge in that, but it's our intention to make this a commodity just like navigating your car should be. And John gave his own version of this. This is ours. If you look at the total amount of data that can be ingested now, organized and curated, the cost is dropping dramatically by the day. But it's not just the biomolecular data. As I said, it's also the social data. I'm equipped with my study watch, which is measuring 17 things. It's not totally there, but if you combine what can be done with sensors that can be worn and cell phones that we all carry around, cognition, balance, activity, social interaction, it's all there in what's been called the digital phenotype. It's a great article that Tom Insel wrote, who's now CEO of a company working on this topic after having been at the NIMH. But then for the large sample trial, I think we need to go to a new version, which is using health system data. We're all now heavily incentivized for business reasons to collect health data, and we're just getting to the point where the data is beginning to get good enough that it can be used for clinical trials. Our own version of this in the US is called PCORnet. There are many versions of it, but this particular one is built on the idea of why not bring together patients who are concerned about their diseases and their families with organized health systems which have a reason to collect the data, coordinate that activity, and get a wheel churning, which is constantly asking questions, not asking just one question at a time, but always deciding what the next question is in clinical practice and trying to get an answer. And we're not there yet, but we do have data now from both electronic health records and claims data for billing on 122 million Americans, about a third of the country. And if we can just get the doctors interested, which is the big issue now, I think our ability to answer questions is going to increase by several log orders very quickly. Now, this was envisioned at the FDA. What if we went from a system where we did each study one-off, one at a time, to a system in which we were constantly collecting the information, constantly interrogating it, asking questions, getting answers, feeding them back into the system, taking advantage of the two-way digital environment that we now live in. And why do I believe this can be done? Because this is the way Google works. And I'm working there half-time. I'm still trying to understand it. It's a little over my head. But a simple way to think about this is in Google's business, if it wants to change something that's integrally related to a computer screen, you're not allowed to change that without doing a randomized trial. Or as they would say it, why would you take a chance on something as important as your business by guessing what the right answer is about what to do? So randomization is built into the Google environment. When you agree to use Google search, you're agreeing to participate in what's called A/B comparisons, which are just big randomized trials done. The dependent variable is not how long you live, it's how much ad revenue accrues over time, or what you're going to click on next, which is a pretty interesting short-term variable. By the way, the real gurus now of marketing and advertising are not just saying what you're going to click on next. It's what are the factors in what you see that will cause you to go from looking at something to clicking on the buy button on the internet to actually buy the item. We need to do this for health, and if we did, I think it would have a big effect. In addition to that, all the analyses don't have to be done in Oxford. We can now do analyses through distributed computing anywhere we want to do them, and I would argue that there's a lot to be gained, particularly as we enter this era of machine learning and other methods, to have a lot of different people looking at the same data and comparing the results that they get. And then finally, in collaboration with Jeremy and Martin, Rory, and others, this is the time to really get involved in the regulatory scheme of how this is going to work. We pretty carefully built in to the 21st century cures legislation in the US and the user fee agreements with the industry to open up the world. Bob mentioned real world data, but the idea here is not just looking at data and trying to figure out what works. The idea is to begin to embed randomized trials within that data. But we all need to work together to figure out how to do that. And then I think independently of what country you live in, we all have computing using basically the same tools. We can really accelerate this effort. So in conclusion, what I'd say is there's no technical reason we can't make the clinical trial system more efficient. We've got to get rid of SCTs. We need to use modern digital information about biology and demand that it be used to get reliable answers in the earlier phases so we don't waste our time and money with a 90% failure rate in phase 3. We need to limit the number of large wasteful trials. There's still a need for some in certain circumstances. And we need to apply the knowledge and practice and iteratively improve practice at a much faster rate than, for example, what's happened in breast cancer that Larry put forward. And this is sort of a plea to get involved right now because the docket is open at the FDA through a whole series of meetings. Not that the FDA is the be-all, end-all, but it certainly has an influence on what happens at the rest of the world. And if we can get that right, I think it'll have a big influence on you all. So I hope that we can take the principles of Richard Peto and apply them at a massively accelerated pace to improve health and healthcare. Thanks.
That's digital revolution. We gotta see some trials done this way.
Good afternoon. Can you hear me? Yeah. Okay. I'm Tom Peto, and I also don't have an anecdote about meeting Richard, although Julian, you've known him longer. I guess I knew him earlier in my life, although you probably don't want to think about that. Anyway, so I'm going to talk about malaria a little bit. That's what I work on, and I probably work on this because of you. Although the two things I want to talk about, first, artesunate suppositories. So these emergency treatment. This is treatment to give children, especially children in Africa who have severe malaria, to save their lives by preventing them dying on the way to get to hospital, or meaning when they get to hospital, they can still be treated. And then the second thing is mass drug administration, which is something which is being piloted. So we don't have, I really shouldn't have been put in this session, we don't have big definitive studies on this. This is something which is under pilot in Southeast Asia as a potential tool for malaria elimination. Rory, I think actually it was you that got me to go out on this study supposedly for 3 months when I was 23, and I finished when I was 30. So it's all right for you guys asking for big numbers, but someone's got to sit in a village and recruit people. Anyway, so malaria should be curable. The main problem is people aren't getting effective drugs early enough to save their lives. And in the places where the deaths are occurring, and as Prabhat has said, we don't know how many people are dying from it still. And the turn of the millennium, it was estimated as something like 2 million, and now perhaps 500,000, but again, we don't know. But we do know a lot of the deaths are in the rural tropics, especially rural Africa, where people don't have access to injectable treatment. So a kid who has a fever, perhaps develops convulsions or becomes comatose or prostrate or is just vomiting, so you can't give them oral medication. They may well have malaria, and if you don't get something into them and there's nothing injectable available, then they may die before they get proper treatment. So rectal artesunate was developed for this. It's not definitive cure. If you just give one suppository, it won't be sufficient, but it may buy you the time for them to get to hospital and get treated. There was a call to do a clinical trial on this, an individually randomized, placebo-controlled clinical trial where kids would either go into hospital as normal, they'd be recruited in villages with a fever, unable to swallow, and would be sent to hospital either having treatment started early or started late. And this was a study led by Melba Gomez and the World Health Organization, supported by many other people, and it was in Bangladesh and Ghana and Tanzania, which was where I was. And up on the top left, you can see Abdul Babika, who was the trial statistician, shaking hands with a guy called Makassi, or Scissors. He was the local Maasai leader. He's 6'7" and had got 25 kids. And we recruited one of them at the beginning. And this guy, like everyone in the district, was terrified of him. And we were just, oh, God, we hope this kid's all right. We were sort of getting ready to leave if anything happened. But it was fine. And then afterwards, when he was our representative, and we carried on recruiting, we got thousands of people in the study, and it ended up being, I think, still the biggest randomized controlled trial of severe malaria ever. That's Dad visiting the village malaria workers. That's the guys on the motorbikes who'd go around and supervise the villages. Yeah, so I was... fresh-faced and 23, and then came back age 30, never been on a publication, years before anything happens. But a proper study was done. I'm not, to this audience, going to say subgroup analysis are the best thing, but in this particular study, we randomized properly. There were large numbers of events, but we saw that in the kids who got to hospital early, because during this study we wanted to do the best by them, and people were encouraging referral. The kids who got there very quickly, it didn't make much difference. But in the population that the suppository is designed to help, kids who are a long way from hospital, in that population, there was a big difference. And it's taken a long time, and this was a big study. It was quite well received. And liked. It's taken quite a lot of time to influence policy, depressingly long. But there is now scale up of this intervention in Africa. The 5 highest burden countries are distributing it. It is properly manufactured and distributed. So it was a long time from beginning to end. But anyway, that was my first taste of being involved in research, and it was really good fun. Anyway, so. This is now 6,000 miles east of here in Southeast Asia, where I live, where the problem is are quite different. Malaria deaths have come down massively, and cases have come down massively, but there's emergent multi-drug resistance, which is a serious problem. Previously, this has spread from Southeast Asia to Africa, and perhaps results in millions of deaths. And in Southeast Asia, this is a major barrier to elimination, which is what countries are trying to do at the moment. And so various different things are being tried. There's improvements in case management. So in Cambodia, which is where I work, that's essentially a village malaria worker program in about 4,000 villages, where you get early diagnosis with a rapid diagnostic test and treatment. Vector control, although unfortunately in Southeast Asia, the mosquitoes, the main vectors, don't bite at night, so bed nets don't work as well, but they do work. I mean, they're still really worth doing. And then other sort of more aggressive measures to try and eliminate rapidly while we have effective first-line treatments, including one thing which we've been piloting, which is mass drug administration. So that's presumptive treatment of everybody in a sort of defined area to get rid of all parasites and interrupt transmission like that. So we had the idea of malaria as being, the visible cases, the top of the iceberg, and then the more sensitive the test you use, the more malaria you see. We did some surveys, us and other groups across the region, and found that out of about 20,000 people, 13% or so have malaria parasites, and that's probably sustaining transmission. So in 4 countries, we did this pilot. And and the next thing, so getting blood from everybody to do these surveys, or getting lots of people to take medicine was quite a lot of work. It's not hard to get big numbers, but to get everybody inside a small area to do something at the same time, I mean, they're individuals, they can choose. So we had to sort of actually live in the villages and put on concerts and get the monks involved and take the medicine ourselves and this is Western Cambodia, so we're sort of hanging out with the old Khmer Rouge Yeah, anyway, it was, so the mass drug administration, I'm going to say that the pilot went well, but also one of the findings was that it was actually quite difficult for us to do it. It was harder than we expected. And there was one point where we had to sort of go out into the jungle and sort of shirts off and drinking with the local old Khmer Rouge guys, and they'd caught this little deer, and then they'd squeezed out its intestine to make this soup. And it was a sort of test of how willing we were to sort of meet on their level, and then they were going to help us. And so, like, people talk about eating shit. We actually did it for that study. I mean, it was disgusting. Sorry, that's not really appropriate. Anyway, and I thought maybe it was like rhino horn, like it'd be some sort of aphrodisiac. So I sort of asked the translator to say that, and the guy was, they talked with each other like, no, if anything, it puts you off. Like, but we got good coverage. We got like 90% or so. Yeah, I'm so embarrassed showing this slide after, especially the last presentation, but all of them, and this is tiny numbers. So it's about 4% of the people in these villages a year would have falciparum before we did our, so we randomized, but the randomization obviously doesn't count for anything with 4. But after we did the MDA, which is 3 months of curative treatment with DHA piperaquine, it's an ACT, artemisinin combination therapy, incidence did drop where you would hope, and then the following year there was nothing, and then with the control villages there was incidence, then it dropped when we did crossover treatment. But it's a pilot study. It's not a definitive study like some of the things you've seen earlier. I think it's encouraging. It'd be nice to see it scaled up, but still, the main thing is early access to effective drugs. Yeah, MDA might be useful in some areas, but this is, well, we were asked to look forward, so please excuse anyway. So this was our gang, and then we got money from Bill Gates to do the study. So he and his wife came down to support us, and then they gave this speech, and then he went on TV in America, and someone messaged and said, oh, he's talking about your study. And he went on the Ellen show, which is the sort of, one of the most watched shows. Have you noticed, like, bastard, it was in that, I'm there, and then when he's on TV, a very petty man. Yeah, anyway. MDA is being piloted. It may be very exciting. Getting rid of drug-resistant parasites in Southeast Asia is really important, and it's really interesting working on it. There may be ways we can improve MDA with different drugs, but anyway, that's not the thing to talk about. That's Richard and Julian. Everyone's been too nice about you, but not me. Actually, yeah. I mean, getting involved in all this stuff, I feel so privileged to have, even from a worm's eye view, worked on these studies, and it's been so interesting. And yeah, it's probably because of you that I've had the chance to do it. So anyway, yeah, thanks.
This is the pointer, and this is...
Yeah, this one goes forward.
Right.
This one goes forward, yeah.
Right. I came to Oxford in 1976 to do a DPhil with Peter Slight, and we designed a trial to look at beta blockers in acute MI with a grand sample size of 100. Now, if you ask me how did we calculate it, it sounded like a good number. And after about 50 people, in which we measured, as Oliver Omrod remembers, 35 lead ECG maps every 6 hours, and after 1.5 years, we had 45 patients. And then I visited Sweden, and Lars Wilhelmsson's here, who are doing a much bigger study of 1,500 people, and they said, go and talk to Richard Peto about designing trials. And I said, who Peto? And he said, and I said, where is he? And he said, he's in your building. So I came back and rang Richard and said, sir, I had my Indian deference still. I said, I need to talk to you. My study isn't going well. and I'm trying to do my DPhil. I've spent half my time. So he said, go away, I don't have time for you. then I said, no, sir, please, I need to talk to you. So he said, okay, I'll give you 15 minutes. Those 15 minutes are still counting 40 years later. And I remember two things from the study, and I agreed to everything. You know, later on he said, Salim, you're one of the few people who argues with me. And he said two things. You've got to get it much bigger, and you've got to make it much simpler. And he helped me redesign it completely. The other thing that I remember him telling me was, I don't care about your DPhil. All I care is that you do something useful. But those were important messages. It wasn't out of lack of anything. Anyway, over the years, we then went on to do a small, elegant study of 480 people with 2 centers collaborating that got published in reputable journals, and it had a benefit on ECG changes and enzyme changes and a significant reduction in mortality, nominally significant. So I told Richard, we've proven it, let's use it. He said, no, now you do the real experiment. Now, this paper that Rory, Richard, and I wrote is about 6 or 7 years of dialogue and discussion. I have never taken a course formally, nor have I taken an epidemiology course, but I have teachers around me visiting Richard after my night calls or weekend calls, and often I was at his home in Great Clarendon Street, and he would teach me about all kinds of things. Now, it was pretty hard to concentrate because I knew that James Bond slept without clothes. I didn't know Oxford academics slept without clothes. It was pretty distracting. Anyway, this paper, although I'm the first author, really the ideas are Richard. And I benefited enormously by working together, but being mentored by Richard. And this paper had only a measly 45 drafts and was a masterpiece. The first and foremost, ask an important question, and second, answer it reliably. That sentence was written and rewritten dozens and dozens of times. That is vintage Richard writing with a piece of paper and a pencil. And I don't know whether he still does it. This then set me off to do various things. I did my clinical training in medicine and then in cardiology, and then got a position at the NIH. I was invited to work on the first large heart failure program in the world. It wasn't necessarily large, but they had a ton of money. And the usual trial in heart failure was 200 or so people. The biggest trial in those days was the VHEFT first of about 550 people with 3 arms. And I had just come out brash from my cardiology training and brash from having worked with Richard. And I had to persuade the United States that we were going to do a trial 10 times larger. And the only way we could do that was a clever trick. We said the main trial is going to be ultra simple, 4 pages of data collection, which you will know in the US is an anathema. But we also said we will do 7 little elegant sub-studies where we can study whatever widget you want to use. We call them sub-studies, and they truly did inform us as well. So this study showed that an ACE inhibitor reduced mortality in people with heart failure and low ejection fraction, and it prevented people getting into heart failure and being rehospitalized. We did something new. We did a parallel study in people with pre-heart failure, that is low ejection fraction. And for those of you who don't know, the heart pumps a certain amount of blood out with each beat, and usually it's about 55% or more, and we call low under 35%. And here we found that although there was a big effect on preventing development of heart failure, there was very modest effect on preventing death. But many years later, after I moved from NIH to McMaster, I knew that study needed to go longer. So we did, through a variety of means, record linkage, and this is the treatment trial where the benefits continued, but then by the time we got to 12 years, 70% of people had died in both groups. But contrast that with what happened to the prevention trial. We only had an absolute difference of 2% at the end of the trial. No more treatment, so both groups were treated equally. It doubled to 4%, and by the time we got to 12 years, it increased by 6%. And so what I learned from this, that is in lower risk individual, trials had to be much longer than we usually design them, and long-term follow-up was useful. But we also asked the question, had we really treated these people longer, would we have gotten a bigger effect? I rather suspect we would. Now, moving to McMaster, I was determined to show that ACE inhibitors also had an effect in preventing heart attacks. In the SOLVE trials, there was a reduction in heart attack. In the SAVE trial done by Mark Pfeffer, there was a reduction in heart attack. But the FDA said, no, we want to prove it. I had to prove it. So we set up the HOPE study in people without heart failure, 9,000 people. This study only cost about 18 million Canadian in those days, which in real money, that's monopoly money, in real money is about 14 million or so US. And we saw a very clear reduction in heart attacks, strokes, and deaths, a clear reduction in deaths, MI, strokes, neutral effect on non-CB deaths, and 16%. And the surprising thing was in these people who weren't necessarily hypertensive, there was only a 3.5 millimeter reduction in blood pressure, which meant, if this was true, that the majority of effects was through non-blood pressure related mechanisms. So, but we had also factored in vitamin E. I mean, what Michael Brown didn't say was an equally important result of HPS was the neutral effects of vitamin E, the antioxidants. And we had tested vitamin E, and there was a neutral effect using a factorial design. And the lessons I took from it was factorial designs were efficient to test simple generic interventions like vitamin E that nobody funds. So about 50% of our trials today involve factorial designs. The other thing we learned is you can do lots of trials, and if you don't get trials with positive results, people stop funding you. So we were lucky to have got a trial that was positive. In parallel with that, I had worked on the ISIS trials with Rory, Richard, and Peter Slight, who I hope will be here this evening. And so we continued the tradition of acute MI, acute coronary syndrome trials. And over the years, we've done 12 such trials in about 40 countries on a total of about 140,000 people. And many of them did have positive results, and it had an influence on science, on practice. But this is the trial that is my most favorite. This started off as a boring trial. It started off by looking at a new agent, fondaparinux versus enoxaparin. And fondaparinux is a tiny pentasaccharide that binds to antithrombin, and then it changes the receptor configuration, and 10A binds to it. This is the coagulation pathway. There's the intrinsic and the extrinsic pathway, and 10A is key. And that should therefore be quite effective. And the fondaparinux then gets released, and you can go back and cycle it. So this was the design, 20,000 people with acute coronary syndromes, half to fondaparinux, half to enoxaparin, the most widely used antithrombotic then in the field. And we had a primary endpoint of death, myocardial infarction, and refractory ischemia 2 days after the end of treatment, bleeds, and deaths. And what did we find? This was a non-inferiority trial. So we cried victory. You know, no difference between the two treatments out at 9 days. But this was the interesting finding, a 50% reduction in bleeding with fondaparinux compared to enoxaparin, and it translated into about a fifth reduction in mortality. So similar effect on efficacy, but a major difference in safety, and that's translating into mortality reduction. And this has started to influence the field, where now just bashing the thrombus isn't enough. You've got to balance it with safety. Now, the other analysis we did, which was a simple numbers analysis, which Richard taught me. Just look at the architecture of the data. And when you look at deaths at 180 days, there were 64 fewer deaths. No difference in those who did not bleed. The entire difference, 95% of the difference, came from the people who bled. Richard once told me, if you do a good trial, you don't need statisticians. The results have to be obvious by themselves. So that was one of them. And the lessons we learned was avoiding bleeding was just as important as preventing ischemic events. And since then, Rob and I and others have been involved in trials with the new oral anticoagulants, and they have been found not only to be more effective, they've actually been found to be safer as well. For instance, there's a 65% reduction in intracerebral bleeds with these new agents. And as they go off patent, these will be used widely worldwide. Now, my passion, because I'm from India, was working in neglected diseases. And I discussed this with Richard many, many times. And he's always said, start with the disease burden. But that doesn't work out often. Opportunities present itself. We've done many observational studies, and I'm not going to talk about that. Includes the INTERHAR, the INTERStroke, and the PURE study. But I'm going to talk about the trials we did in neglected conditions. We did TB pericarditis. It has a 50% one-year mortality rate in the people who get the condition. Because when they get it, there is fluid around the heart, and then it constricts, and both of them kill people, especially if you're living in a place where you have no access to health care. So Bongani Mayusi from Cape Town, along with 18 other centers in Africa, it was a really tough study to do. We did the study, factorial design with steroids, which was the standard therapy, and TB vaccine. Both were ineffective, although steroids prevented vasoconstriction, but they substantially increased HIV cancers. The previous trials of steroids was 180 people in the pre-HIV region, and we had something like 16 cancers versus 2 cancers. Now, you'd say they aren't big numbers, but in the context of lack of efficacy, that was enough to change practice. I'm going to talk a little bit about Chagas disease, where we've invested over 10 years of work, and I'll briefly mention rheumatic valve disease is one of the biggest curable heart diseases in the world. Affects about 400,000 people die a year. Most of the deaths are in people under 25, and most of those are preventable. And we have a program of a large registry of 20,000 people, and registries can teach you a lot. And in that, what we found is that the commonest recommendations is to give penicillin to prevent recurrence. But what we're finding is recurrent acute rheumatic fever is only 1% per year. But the commonest cause of death is heart failure, which is 8% per year. And the valvuloplasties or surgery that people need just isn't happening in sub-Saharan Africa, happening more in South Asia. We've also managed to got a trial called Invictus going on 4,500 people with valve disease and atrial fibrillation. Thanks to Bayer, due to their corporate social responsibility, that trial is halfway through. Compared to the usual therapy, or warfarin, and the problem in Africa is warfarin control is terrible. Labs are far away. People have to walk a day to get these things done. And so this trial is ongoing, and the centers that are participating are among the better centers, yet INR control isn't great. Polypill has been one of my passions, and we've done 2 phase 2 trials to find the right dosing and combination, and they were published in the Lancet in Circulation. And now, thanks to the Wellcome Trust, we have a large trial in high-risk primary prevention, which I hope will report in about 2 years. And hopefully, if it's possible, Tom Frieden might want to take the Polypill into his program. Now, Chagas disease, and this is the last part of my talk, and this has left me confused. For those who don't know what Chagas disease is, it's caused by trypanosome, Trypanosoma cruzi, which is like the same family of organism that causes syphilis. And it's endemic in parts of South America, affects 8 million people. Its acute infection resolves in 50%. What it is, there's a bug in the roof, and it falls on people, defecates on people, bites them, and rubs the feces into people, and the stuff gets in. There's an acute phase where you can have something called Romanos sign, where the eye swells, but then mostly it resolves. But 1 in 3 people in the chronic phase get cardiomyopathy, and 1 in 6 people get dysfunction of the gut called megacolon. Anyway, in the acute phase, benznidazole, the only marketed drug for Chagas disease, is very effective. But in the chronic phase, there's no evidence, and people sort of assumed that it would work. And there were data that in the chronic phase, if you did PCR, you can identify the bug in the blood. So we set up a study of nearly 3,000 people from 50 sites in 5 countries. Half came from Brazil, half came from 4 other countries. We had a local coordinating center in Brazil. We had to set up PCR collabs. This is the biggest PCR effort in Chagas disease there. And the study, unfortunately, with a mean of nearly 6 years of follow-up, did not show a clear difference. We had also a careful echo study, because you would think that the ventricular function would be affected, and there was no impact. But the study generated controversy because we were going against the tide and saying the only treatment that's available doesn't work. And to add to that, there were subgroup analyses. And this is the subgroup analysis on PCR negativization by country: Colombia or Salvador, Brazil, Argentina, Bolivia. Now, in Colombia and Salvador, type 5 bug is the commonest bug, and you have high parasite loads. In Brazil, type 2 is commoner, and the parasite loads are lower. And Argentina and Bolivia is in between. And as you'll see, in Colombia and Salvador, with rather good numbers for PCR, there's no effect. There's a very big effect in Brazil and an intermediate effect in Argentina and Bolivia, and this is the p-value for interaction. So no matter what you say, that's a pretty impressive subgroup analysis on the PCRs. So when we looked at clinical events, actually, we partly saw something that mirrored it. In Brazil, there's a nominally significant reduction in the primary endpoint. And in other countries, there wasn't. This is the outlier, because you would have expected some benefit there, but we didn't see it. And this led to 2 years of debate in writing the paper. The Brazilians said it works in Brazil. Everybody else said you've got to look at the overall result. Now, we said, look, the analysis by country is crude because parasites don't carry passports. So if you think they matter, then let's do genotyping. So right now we are genotyping the parasites from the stored blood, and we'll repeat the subgroup analysis to see what happens. We are now thinking of a new trial with multiple cycles of benzimidazole, because what we gave was 60 days of treatment only. This may be like TB. You may have to give prolonged treatment, or like chemotherapy. So we are experimenting with that idea. We evaluated newer trypanosomal therapies like posaconazole. They seem to be very effective acutely, less side effects. The benefits didn't persist long term. So, and we did combination as well. And maybe in chronic disease, we need therapies that aim the myocardium rather than the bug alone. Now, over the 40 years I've collaborated with Richard, there are many things I've learned, and I hope I put some of those to use. That is, start with disease burden. Now, I didn't quite do that. I took the opportunities and worked on it. Get the big picture right and get every detail right. Now, in a sense, that's what everybody here said in different presentations. Place the results in context. Your trial is not alone. Put them in the entire context. Incidentally, that large simple trial paper that Richard, Rory, and I wrote actually had all the key principles on how you do a meta-analysis. And also the first 2 papers that we wrote, which I haven't shown you, beta blockade and streptokinase, were the first 2 proper systematic overviews in the field. Tom Chalmers had done pooling, where you add up the events on the 2 groups, but this was the first time proper methodology was used. And obviously, Richard has taken it further in the breast cancer area, and Colin Bajan and others in the lipid lowering and antiplatelet. The other thing he kept on reminding me is, your study must be the definitive word on the issue. It must be so large, it drowns everything else out. Now, he tried to do that with vitamin A, with the study he did in India with Shelley Avasthi, and it is by far the biggest in the literature. There is some controversy because the results were different from the rest, but, what can I say? I believe Richard when in doubt. Then he also said unanticipated qualitative interactions are rare. This is the hardest one for those of us in clinical trials to accept. You have to almost believe it like a mantra. And by and large, I tend to believe it, except when I see results like the benznidazole results that we saw. Maybe there is something there based on the genotype of the strain. We don't know that yet. And so I will say the last 40 years with Richard has been nothing but a miracle. It's been a miracle in many ways. It's wonderful to see the impact of what he himself has done. It's even more fantastic to see the impact he's done through the people he's mentored, like Rory, me, John Dinesh, so many other people who are here, and they've multiplied. And I've also had a personal minor miracle over the last 40 years. I was very ill at a time in Oxford, and Richard, Rory, Peter, and others were strong friends and got me through. Thank you for both the science, and thank you for the personal support and comfort. Thank you very much.
This is on, is it? So, Richard, you're almost done. If I could just turn to the title I was given, not asked for. My name's Jeremy Farrer, Head of Welcome. End notes. Why do we still need Richard Peto? Question mark. Not a Richard Peto, not another Richard Peto, but Richard Peto. I'll come back to that at the end. So, Richard, we know how much you've really enjoyed and looking forward to this meeting, and how relaxed you've been in the months of its gestation, how you didn't give a toss who came or what they spoke about. You didn't want to interfere or get involved. You left it up to your people who have followed you, just like you left all of those papers, hundreds over the years, those final drafts. When I first went to Edinburgh to sort of work in neurology, somebody there told me that you were the most irritating person to redraft a paper with. They are in the room if you want to get back at them. Neurology, Edinburgh. I'm only going to say one really slushy thing, Richard, because you've heard it all day and you must be tired of it, even you. I don't know everybody in the world, but of those people I do know, I don't know that I know anybody else that has enhanced the lives or saved the lives of so many human beings. Not only through your own work, which is obviously phenomenal, but actually through those that have followed you, those you've irritated. You've heard quite a bit of that today. Those you've inspired, those you've challenged, those of you who you've inspired to think bigger than they would have thought themselves. Actually, it's not what you've achieved, huge as that is, it's what others that you've mentored have gone on to achieve. And actually, I think that is the true mark of greatness. You've enjoyed that success as well, and that is a rarity. Most people, as they go through their career, and dare I say it, get a little bit older, become more grumpy and suffer fools less gladly. That was never a problem with you because you were grumpy at the start. And unfortunately, given the world is made up of fools, most of us are fools, you were never going to suffer them less. So grumpiness and suffering fools has never been your great strength. But the one thing you haven't done is been insular. You haven't become inward-looking. You've embraced new things as they've come along. You may have disparaged them to begin with, genetics or omics, or ways of measuring biology, but you then have incorporated them into your own work, and you've made them better because of that. You have remained open, and most importantly, you've remained curious as a child, like a child. So as I did a canvas of opinion over the coffee break, and then we met in the teachers' common room before coming, I'd like to say that most of us believe you do deserve a B+. Your Latin needs a bit of work. Sometimes in maths you do jump to the answer without showing all your work. We'd really like you to pay a bit more attention if you could. And we would really like you to at least give the impression of showing respect to others, your teachers, your peers, even if, yes, they are fools. And whatever you do, please don't try and drive and talk at the same time. It's dangerous to you, and it's dangerous to your passengers, and it's dangerous to humanity. So please don't. And if you could spend a little bit less time in the table football team, please do. But I'm going to give you 3 challenges as you go from middle school to high school, Richard, because I think these are 3 really profound challenges. In your period, your professional career, you've gone through a honeymoon phase. You may have helped that by the work you've done. But we are at risk at the moment of turning clinical research generally into something that's almost impossible to do for anybody young and anybody without a huge amount of funding behind them. We have to turn, as Rob described earlier, we have to turn the tide of what has become a bureaucratic nightmare in order to achieve. And if we don't turn this tide, the next generation of Richard Petos will not go into this space because they'll go into other things because it's easier to do and it's easier to forge a career. I think you need to use your voice in arguing for that, and don't underestimate the power that your voice will have in that. We are committed to doing that at Wellcome and with colleagues in this university and at Duke with Rob, but it does need other people to make that case for it. Secondly, we have been through a period of relative scientific enlightenment, I think, over the last 30, 40, 50 years. That is in danger from coming nationalism and coming questioning of experts. You are one of the sort of examples of experts, and I think we have to fight back against this, and I think as you move to the high school, it would be good if you could use your voice not amongst those that are like you, but amongst those that are not like you. If we don't watch, nationalism will drive us to a different direction, scientific experts will be misjudged, and the world will be a worse place for it. And finally, what is your advice if you happen to be head of a funding agency that we can do to address the first 2 issues? I don't want an answer to that, Richard, but I suppose I should ask for one. So yes, I think in answer to the title I was given, do we still need the Richard Peto? We don't want a Richard Peto 2, we don't want a Richard Peto Light, although Tom, that was a great talk. So the answer to the question I was given is yes, we still do need a Richard Peto, not to shy away, not to step away, not to loosen that voice. We still do need that voice. And in fact, I would argue we need that voice today more than we've ever needed it before. Thank you. You coming up?
I don't think that decision was justifiable. And I think that often, if you did support people early on, then in many cases it would not be successful. It wouldn't actually piece things. I think I did do some things because I was supported earlier on, and I would like to see the pressures on young people now, postdocs now, or postdocs are just ridiculous, and it's corrupting. It actually corrupts them. I'd like things like readerships, associate professorships, something or other to just give some people some kind of security. And I think the same with groups. If the Medical Research Council, I won't talk about what the Wellcome Trust should do, but say the Medical Research Council, if they were to divide up their research budget and to set aside, say, 1/5 of it for continuation funding, where basically
groups just describe what they've been doing over the last 5 or 10 years and the extent to which this is still relevant, using citations which aren't citation counts, which are not a perfect index. At least the past is real. When you're actually writing the future of what you're going to do in advanced application, mostly it's bullshit. When you're going to do a particular project, it isn't, but mostly it is. If there were money set aside for the continuation of groups that have been productive in the reasonably recent past, and maybe with a set amount of money, so you don't even have to justify the amount of money. If you look back on it 20 years later, if you look back on the amount of money spent on this and on the other run process, then it might well be that you'd actually achieve more with 1/5 which you set aside for, in a sense,